Hello, everyone. So this is the second video on the topic of Myhill-Nerode theorem. So in this video, the goal is to understand one of the fundamental constructs in set theory, namely an equivalence relation, which will prove to be very useful in our study of the Myhill-Nerode theorem. So before defining what an equivalence relation is, let's just recall what a relation is. So for a set A, capital A, let's call it the ground set, a relation R is nothing but a subset of the Cartesian product of A with itself. In other words, a relation R is nothing but a subset of ordered pairs of elements which come from the ground set A. Now, as you can see, the notion of a relation is extremely general, and in general, and as such, given it is so general, it's essentially unuseful. So we impose a few more restrictions on the notion of a relation to make it useful. And we arrive at the definition of an equivalence relation. So what's an equivalence relation? So an equivalence relation is nothing but a relation R, again on the ground set A, which satisfies three axioms. First is the axiom of reflexivity, which just says that whenever consider any element little a in the ground set A, then A comma A is in the relation R. So among other things, this implies that an equivalence relation can never be empty. It at least has some elements. Second is the notion of symmetry, which says that if A comma B is an element of R for elements A and B belonging to the ground set capital A, then B comma A is also an element of R. So in other words, what you get here is that even though we defined relation R to be a subset of ordered pairs over the ground set capital A, as far as an equivalence relation is concerned, the order is immaterial. Okay, and the third axiom is the axiom of transitivity, which says that if A comma B is an element of R and B comma C is an element of R, then A comma C is also an element of R. So that finishes the definition of an equivalence relation. And equivalence relations can be found all over in mathematics, and certainly in discrete math, but also in continuous math. And let's see an example of an equivalence relation just to make sure that we're on the same page with this definition. So one particular example is the notion of connectivity in undirected graphs. So let G equal to V comma E be an undirected graph. So what do I mean by this? I mean that V is the set of vertices and E is the set of edges in this graph. And remember, the graph is undirected. So now for this graph G, we define the notion of a relation R sub G. This will be an equivalence relation, which we define now. It will be defined on the set V. The ground set is the set V of vertices. And X comma Y, two vertices X comma Y, are said to be in this relation R sub G if in the graph G there's a path from X to Y. So there's a way to go from X to Y in the graph G. And the claim is that this relation R sub G for an undirected graph G is an equivalence relation. And we now verify the axioms of an equivalence relation. So let's verify the first axiom. The first axiom is that of reflexivity. So which is just we need to verify that whenever X is a vertex in the graph, X is an element of V. Let's verify that X comma X is in RG. And this is easy to check, right? Because whatever be a vertex X, there is always a path from X to X. Because you can always go from X to X for a path of length 0. Okay. So reflexivity, the axiom of reflexivity is satisfied. The next axiom is that of symmetry. So we need to verify that if X comma Y is in RG, then Y comma X is in RG. And this is again easy to check, because if there's a path from X to Y in a graph G, then there's also a path from Y to X, because you can always retrace the steps in an undirected graph. And this is where we use the notion of undirected, the graph being undirected, crucially. This is not true for directed graph. And the final is finally we check the notion of transitivity, which just says that if X comma Y, so we need to verify that if X comma Y is in RG and Y comma Z is in RG, then X comma Z is in RG. And this is again easy to check from the definition of a path. If there's a path from X to Y and there's a path from Y to Z, then there's also paths from X to Z. You can go from X to Y and then Y to Z. Potentially there's a simpler path, but there's certainly you can go from X to Z. So this verifies that the relation R sub G is also transitive. And there's in summary, R sub G is an equivalence relation. Having seen the notion of an equivalence relation, now let's associate something called an equivalence, a particular construct called an equivalence class can always be associated with an equivalence relation. So let's see what it is. So let R be an equivalence relation on a ground set capital A. Then for any element X in A, we can define an equivalence class called X sub R or bracket X sub R. So this thing, which is defined to be the set of all elements Y such that X comma Y is in R. So the equivalence class of X in context of the relation R, which we denote by the square bracket X with a subscript R, is a set of all elements to which X is related. Okay. And okay, so first of all, this will also explain where the name equivalence relation comes from. So the first observation is that if X and Y are related, if X comma Y belongs to R, then the equivalence class of X is equal to the equivalence class of Y. Again, I'm not constantly saying equivalence of class of X with respect to R. With respect to R is understood in this context here, but so I'm not going to always say that. But the main thing is that if X and Y are related, if X comma Y is in R, then the equivalence class of X equals the equivalence class of Y. Why is this true? So observe as a standard, observe as is, pardon the interruption. Pardon the interruption, please. Sorry. So let's get back to this thing. So observation, if X comma Y is an element of R, then we want to show that the equivalence class of X and Y are the same. To show this, observe that it suffices to show that the equivalence class of X is contained in the equivalence class of Y. Note that if we manage to show this, then we can also show by symmetry that equivalence class of Y is contained in equivalence class of X, which would thus prove that equivalence class of X and equivalence class of Y are identical. Okay, so how do we show that the equivalence class of X is contained in the equivalence class of Y? Well, so consider any element Z in the equivalence class of X. This is the same as saying that X comma Z is in R. Now, by definition, X comma Y is in R. So by the symmetry axiom of equivalence relations, Y comma X is also in R. And then by the transitivity property of an equivalence relation, by combining X comma Z is in R and Y comma X is in R, we derive that Y comma Z is in R, and thus Z is in the equivalence class of Y. So any element Z which is in the equivalence class of X is also in the equivalence class of Y, thus showing that the equivalence class of X is a subset of the equivalence class of Y. By symmetry, you can also show that the equivalence class of Y is contained in the equivalence class of X, which will show that the equivalence class of X and Y are identical. So in other words, now you can see why the name equivalence relation comes. It says that if X and Y are related, X and Y belongs to X comma Y belongs to R, then the set of all elements which such that X comma Y is in R, if we define this as the equivalence class of X, then whether you consider now define the equivalence class of Y, these are all same sets. So somehow one should interpret this as saying that up to the relation R, this elements, the element X, the element Y, and every element contained in the related to X or related to Y via R are all equal, really. So that's roughly the notion of where the name equivalence relation is coming from. Okay. Now, a very important property is that an equivalence relation R induces a partition on the set A in the following manner. If you consider this for every element X in the ground set A, if you consider the equivalence class of X, this defines a set of elements. This system of sets, this collection of sets, is a partition. It partitions the whole universe, ground set A, into disjoint subsets whose union spans A. Okay, so it partitions A. How do we, so let's check that this is true. Let's verify that this is true. So to verify that some collection of sets is a partition, what do we need to verify? The first thing we need to verify is that every element belongs to at least one collection. Well, that is easy to verify because the element X always belongs to the equivalence class of X. So if you consider the collection of sets, which is given by the equivalence class of X as X ranges over A, it certainly covers every element. And now we need to verify that this collection is disjoint. So suppose it's not disjoint. So suppose consider two sets, consider two elements X and Y such that the equivalence class of X and the equivalence class of Y intersect somewhere. So let Z be an element which is in the equivalence class of X and the equivalence class of Y. What does that imply? That implies that X comma Z is also in R and Y comma Z is also in R. But then by transitivity, by applying symmetry, you will get, by applying symmetry and transitivity, you can easily derive that X comma Y is in R, which by our earlier observation, namely this observation, the one I'm highlighting in yellow, shows that the equivalence class of X and the equivalence class of Y are identical. So it means that if any two sets in this collection equivalence class of X intersect, then they're basically the same sets. Or in other words, of course, like, so in other words, no two sets intersect non-trivially. If two sets intersect at one point, they are the same set. So if the only way equivalence class of X and equivalence class of Y share an element is because they're the same sets. Or in other words, you can think of calling some set equivalence class of X is just a renaming of calling it equivalence class of Y. Okay. So this proves that the equivalence equivalence relation R induces a partition where the sets of the partition are given by equivalence class of X as X ranges over A. And again, it's important to emphasize that many sets in this collection of sets equivalence class of X as X ranges over A are identical, are the same. So they're just renamings of each other. So we might be naming a set more than once, calling it equivalence class of X and also calling it equivalence class of Y if X and Y are related. But up to renaming the sets and naming several sets at the same time, naming the same set several times, these sets form a partition. So just a picture, like, if the red thing is the universe A, the ground set A, then you can think of equivalence classes as partitioning the ground set A. Let's say in this example, into 5 parts. The first one is the ground set equivalence class of X1, which I just made yellow. The second part element of the second set in the partition is the equivalence class of X2, which I now did yellow. Similarly, equivalence class of X3, X4, and X5. So for example, the one I'm making orange right now consists of all elements. It's the equivalence class of X4, which consists of all elements such that X4 comma, it consists of all elements Z such that X4 comma Z is in R. Okay. Now, equivalence relations for our purposes can be divided into 2 parts, and this is very important. Those equivalence relations which induce a finite number of equivalence classes, for example, in the picture here that we have drawn, this equivalence relation has 5 equivalence classes. And then there are those equivalence relations which have infinite number of equivalence classes. This distinction is going to be very important for us. So of course, for example, in a graph, the graph equivalence relation RG that we saw earlier, this is a finite equivalence relation, partially because the set itself is finite, so you cannot have infinite number of equivalence classes. If the ground set V is finite, you cannot have infinite number of equivalence classes. But as we are going to see examples of equivalence classes, equivalence relations such which induce infinite number of equivalence classes. And this distinction between finite and infinite is very important in the context of Myhill-Nerode theorem. The final thing I need of this final definition I need is the notion of refinement of partitions. In particular, if R and R prime are two equivalence relations on the set A, such that whenever x comma y is in R, x comma y is also in R prime. So any two elements which are related in R, they're also related in R prime. Then we say that R is a refinement of R prime. The reason we say this is that so let's see an example. Let's see example of two equivalence relations, R1 and R2, and observe that in this picture, R1, whenever two elements are related in R1, say x1 and x2, say any two elements which are related in R1, let's say this element and this element, actually, let me use a different marker. So let's say an element, these two green elements I'm marking now, they're related in R1 because they belong to the same equivalence class in R1, namely they're both related to x1. Then they're also related in x2. Okay. Of course, the reverse is not true. For example, the elements x1 and x2 are both in the same equivalence class in R2, but they're in different equivalence classes in R1. And that is why we say that an equivalence relation, whenever this thing holds good, we say equivalence relation R1 refines equivalence relation R2. The reason we are calling it a refinement is because it's inducing, the equivalence relation R1 is inducing a finer partition than R2. Okay. So for example, okay. And so an obvious corollary just of this definition is that if equivalence relation R1 refines R2, then the number of equivalence classes in R1 is at least as large as the number of equivalence classes in R2. The reason being that you're only making the partitions finer. R1 only makes partitions in R2 finer. What R2 does is that it may two partitions which are different in R1 may coalesce in R2. For example, that's what happened to the partitions in R1. Okay. And so it might happen that equivalence relation R1 is infinite, has an infinite number of equivalence classes, and equivalence relation R2 has infinite number of equivalence classes. And then this corollary might not make sense, like what do we mean by the number of equivalence classes? But as long as at least R2 has finite number of equivalence classes, you can always say that the number of equivalence classes in R1 is at least as large as that of R2. R1 might have infinite number of equivalence classes, but if R1 also has finite number of equivalence classes, then the number of equivalence classes in R1 is at least as large as that of R2. And this is basically just the obvious corollary of the definition of a refinement of equivalence classes. So with that, let me conclude this lecture, but let's just recap what we saw. So we started with the notion of equivalence relation. We defined what an equivalence relation is as basically a relation which satisfies three axioms: reflexivity, symmetry, and transitivity. Then we defined the notion, we saw an example of an equivalence relation, namely the connectivity in an undirected graph. We followed it up with seeing the notion of equivalence classes, which are induced by an equivalence relation. And we saw how an equivalence class, an equivalence relation via equivalence classes induces a partition of the ground set A. We said that there are two different kinds of equivalence relations, those which induce finite number of equivalence classes and those which induce infinite number of equivalence classes. And this distinction is important, going to be important for us. And we ended with the notion of an equivalence class refining another equivalence class, and what it means for the number of equivalence classes induced via the first equivalence relation vis-a-vis the second equivalence relation. So let's conclude the lecture now. Let's conclude this video now rather. Thank you.